I'm Kendrick Hardison, and this research deals with a rank sums test for significance and difference in copy variation. The background of this is dealing with copy number variation, also known as CNV. CNV is used to detect genetic diseases. A researcher or a clinician will use your DNA or your blood sample and put it on a chip that might look like this. And each chip has a number of case sections, and each case section, in this case 15 case sections, will give off a measure of value according to whatever your genomic DNA says. The way we'll get a data is something like this. We'll have a subject or test subject compared to a number of controls. That number of controls is going to be an N value. And then our rows are going to be the different case sections that we're going to test for. So if I was a test subject, so to say, we'll go from here to this part right here and go to the chip and go to S sub 0.1, and then we'll get a score. Let's just say I got a score of 6.7. And then we're going to go to S sub 0.2 and S sub 0.3 and get those. And then we're going to do the same thing for all the control values and get those values also. Then this brings us to the ranked sum statistics of R. Once we have our scores for each column and each row, we're going to rank them amongst each section. And the lowest rank, or the lowest value is going to get the 0th rank, while the highest value is going to get the number, the N controls. So, for example, for the test subject, if they got a score of 8.8, and then control number 4 got a score of 9.0, 4 will get the 5, and then the subject will get the 4. And then the next section, for section 2, the subject had a score of 9.3, which is the highest out of all those. So they're going to get a score of 5. And we're going to keep doing this, do each section, in this case for section 3 and 4, and get all the way over here. And then once we get all the ranks, we'll sum those ranks to 18. And then you see the next highest is going to be 11. The question is, what makes 18 so special? Or in this case, if the subject and the control are really the same, what makes this 18 so surprising? This brings us to the probability of R equaling 18. And we can find it by saying how many distinct solutions are there for a rank sum of 18 to be given from 4 sections and 5 controls. And if we had, since there's 4 sections, it's going to be 4 numbers add up to each other. We know that we can have 2 4s and 2 5s, which, if order matters, it means it's 4 choose 2, and that's 6 ways. Another way is having 1 3 and 3 5s, which is 4 choose 1, having 4 ways. So there's 10 distinct solutions, but we have to divide this 10 by the total number of possible solutions, which is n plus 1 to the k power. And that's just for the rank sum of 18. But what if we had a rank sum of 19? So to say, then we already know that we already have 1 4 and 3 5s, which is just going to give us 4. And then for R equals 20, there's only one possible way, and that's if you had all 5. Now, we'll see that the p-values for these are, once you actually find this part out, it's going to keep getting smaller and smaller. And this brings us to the notation of the distinct solutions, which is right here, which is the same thing as this 10 right here. And then another way to find that same way of doing it is using this recursive formula. But the interest of that, using Mathematica, the easiest way is to expand this polynomial out right here and take the x to the r term, and whatever that coefficient is, it's going to be the number of distinct solutions, which is 10 in that situation. And I gave an example right here of that same situation. And you see when you're looking for 18 for R, 10 is that coefficient. And when we talk about the exact distribution of it, we're going to use this formula right here once we sum up all the ranks and get that rank sum of R, which is going to be that over there. But research done by a man named Lafrenbach modified the Irwin-Hall distribution to approximate this null distribution. And here's the formula for that. As you can see, if you compare both distributions, the Irwin-Hall is the continuous one, and the exact is the discrete one. Now, as you can see, they do not match at all. This is the case for n equals 6 and k equals 6. And we can go even further to say, if a researcher was using this Irwin-Hall distribution, they're going to reject the null hypothesis whenever the rank sum is greater than or equal to the Irwin-Hall critical value. And as you can see, in this case, Irwin-Hall critical value is going to be right here. If we was testing for alpha value of 0.05, but if they was using the exact distribution, this would be the critical value. As you can see, it would be rejecting differently. Which brings us to the part that if you was using the Irwin-Hall, you're gonna have a if you're using Irwin-Hall, you're gonna have a probability of this much being wrong if you put that same coefficient or that critical value into the exact distribution. And if you was to try to see of all the Irwin-Hall rejections, what percent will be rejected wrongly using the exact, that'll be this one right here. And as you can see, if n equals 10, but if we kept k at 5, but n equals 10, this would be 45% of the time that it's going to be rejected wrongly, while when we have increases to 10, it's going to go all the way down to 6. So it's kind of a good thing if you increase your number of controls that you're testing for. And as for power, when we're dealing with power, we're going to have to, well, in this case, since we simulated all this, the number of controls that we have in this case, 6, is going to be clustered in all of this. And then the subject was right here. Since I had a delta value of higher, so this means, if you don't know what power means, think about this. If I told you I did not take any math classes a day in my life, would you believe it? If I told you I took 15 math classes, it's more believable, right? So power is saying, or detecting that lie. And this is where we get to right here. If we kept k at 7 and n increasing up, we'll see that the power for both the Irwin-Hall and the exact is going to converge to a value. But as you can see, if you had a low amount of controls, that's a big difference, at least 12% of a difference right there. And if we increase the number of controls, if we increase the number of k sections and kept the controls the same, we'll see that power is going to increase over time. But even though it's increasing over time, the Irwin-Hall is constantly above the exact distribution. So all in all, using the Irwin-Hall distribution, we know that you're going to reject the null hypothesis way too quickly. And as you increase the number of n controls, the probability of Irwin-Hall wrongly rejecting is going to decrease. And both the powers of the Irwin-Hall and the exact is going to converge to one value. And as you increase the number of k sections, your power is going to increase over time. But again, the Irwin-Hall is going to have a higher power than the exact, but that power is going to be wrong. So if a researcher was actually going about saying, oh, my power for this is this much, but their power is actually that much in this case. So for k equals 10, you'll see this power right here, 23 and 20, is actually going to keep going up like that. And that is it.
Okay, questions for Kendrick?
Do you have any idea when they actually do these genomic studies what the typical values for N and K are?
They're going to be, from the research that I've read so far, the number of controls is usually always bigger than the number of sections they're testing for. So the number of people they test is going to be a lot bigger than the number of controls or the number of sections. And from what I saw, it's usually 50 to 100 maybe for the number of people. It can go higher, but that's all I've actually seen. It's 50 to 100.
So for those typical values, is there how big is the disparity between your exact results and that approximation? Do you have any idea?
For what part?
So you were showing these comparisons between the power for the approximation and your exact result, and I'm just wondering, like, where typical experiments lie. Is it along the part of the curve where those two have converged, or is it along the part where they're different?
If K was kept the same or kept at this low point like 7, and you increase N all the way up, then they'll be close to each other.
So I guess I can't really exact. You said n is usually 50 or 100, or?
Yeah, in this area from here to here. So I mean, usually it's going to be that close.
Is k equal 7 a pretty typical value?
No, I just use that for an example.
Okay.
Because if you using mathematical, it takes a long time if you increase k.
So it just, there's a lot of variability.
So we found cases where the critical value, so the two right columns, the critical value differs by 4 or 5 or 7. As n gets big, for Irwin Hall, the observed probability of type 1 error converges to 0.5, the nominal. Converges to the exact distributions of type 1 error.
Yeah.
Right? But two things. One, if n is not big, then there is a large probability that you'll get a value of r that would lead you to reject under Irwin Hall, but not under the exact distribution. But moreover, if n increases, the proportion of Irwin Hall rejections that are false rejections. That's not the same as the probability that Irwin Hall wrongly rejects, but the proportion of Irwin Hall's rejections that are bad rejections under the exact distribution increases very slowly. So it takes a much larger n to absorb that.
Kendrick, could you please put up the plot that shows, it looks like a Gaussian type of distribution that compares the Irwin Hall with the exact solution? Yeah, right there. So could you explain why, and again, this is a very naive question, but could you help me understand why the two agree best at the tails but worse at the peak?
I
I'm not sure that's true.
Well, I just look at the curve and the dots seem to match better at the tails than they do at the...
Not relatively.
I mean,
Yeah, relatively.
if I zoomed in, it'll look way.
So the percent
If you're
difference.
thinking about sweeping out area,
Uh-huh.
right, I mean, I'm sure there's a bigger absolute error, but I'm not sure there's a bigger relative error.
Okay, any other questions for Kendrick? All right, let's thank him again.